Okay, looks like we are recording. So I'm going to be going over the first free response question that I gave you guys for the equilibrium unit. So this is taking a bunch of the stuff that you've learned so far and trying to put it together with some calculations and theoretical questions in the format of a free response question from a previous AP test. So here's the first question. We have solid carbon and carbon dioxide gas are reacting to produce carbon monoxide gas. Notice that in the balanced equation, our coefficient for carbon monoxide is 2, whereas the coefficient for carbon dioxide is 1. So 1 mole of carbon dioxide combined with solid carbon gives you 2 moles of carbon monoxide. It says that these are placed in a rigid 2-liter container at 1,160 Kelvin, and this reaction occurs and the pressure is monitored. So for reactions with gases, first of all, any solid that's in the container is, the volume of that solid is considered to be minimal, and we do not need to consider it for this question. So we are just looking at the gases. So we have basically one gas turning into another gas for the purposes of thinking about our reactants and products and their pressures. So we're monitoring total pressure. It says when equilibrium was reached, there was still some solid carbon remaining in the container. Think about why that might be important for a second. All right, so the reason that they mention that in this question is that they want to make sure that you know that the solid carbon was not the limiting reactant, that it is possible at equilibrium for all of the CO2 that was going to react with the carbon to react and become carbon monoxide. So if there was not enough solid carbon remaining, then it would be more difficult to do these equilibrium, we wouldn't be able to do the equilibrium calculations in the same way. But we're assuming that we have enough of our solid carbon that any amount of the CO2 that we start with could react at least to equilibrium. Okay, and then they give us a table of results. And this is pretty typical for a lot of the free response questions. They're going to give you some experimental data and ask you to work with it. So we have time in hours from 0 to 10, and we have total pressure of gases in container. And it says that's in ATM, so that's atmospheres, so that is the unit of pressure that we are using for this problem. So what I want you to see here in this table is that we have a starting pressure. And at the beginning of this experiment, that starting gas pressure was entirely the carbon dioxide. So we started with just the carbon dioxide gas. So that is the pressure of our initial amount of carbon dioxide. And that's going to come up later. And then I also want you to see how this, this reaction progresses. We see an overall increase in total pressure. I want you to think for a second about why you would see an increase in total pressure with time. So the reason that you want, that you're going to see an increase in total pressure goes back to what I was telling you about the coefficients here. Sorry, let me put this here. Our coefficient here is 2 moles of carbon dioxide for every 1 mole of carbon monoxide for every 1 mole of carbon dioxide. So since we're starting with this and ending up with at least some of this, we're going to have a total increase in the number of moles of gas in the same volume, which is going to increase our pressure. So it is not surprising that we're seeing an increase in the total pressure of the gases in a container as we go along. The last thing I want you to notice about this table is that the final two values are the same. So this is kind of like the experiment that we talked about at the beginning of the year where you're getting rid of waters of hydration. This is the one that was similar to the magnesium oxide lab, but we didn't do it. We did a free response question about it. So in that experiment, we were testing the waters of hydration of a salt crystal, and by essentially heating it until, and as we heated it, the water would eventually boil off, leaving the solid crystal behind without basically an anhydrous solid crystal. And so you would continue testing that until your last two measurements were the same. And it's also similar to the neutralization of acid and base that you guys did recently, where you at least kept the your temperature recordings going until you had more or less a flat line. Okay, so what's important about these last two is that we have reached equilibrium, because in the course of 2 hours, the total pressure and therefore the mix of these two gases did not change. Had the mix of these gases changed, because there's 2 moles of one and 1 mole of the other within the reaction, this amount of pressure would have changed. Okay, so this tells us that this is our equilibrium pressure. And this is our starting pressure. And this is going to be just the pressure of the carbon dioxide. Oops, sorry. Our CO2. This is going to be our P total, which is going to be our carbon dioxide plus our carbon monoxide at equilibrium. Okay? So that is what we are given. So we have this container, we have the gases, we have a gas reacting with a solid to produce a different gas. So then we're getting a mixture of gases at the end. Okay, so let's look at the first question. So the first question, A, says, or the first part of the question. These are all going to be very long multi-part questions. They're both considered long free response questions according to the AP format. And when I say both, I mean both of the ones that are going to be on the test that you're going to be taking. So I've just copied the equation up here for us and the basics of what we've been told. And so the first question is to write an equilibrium expression. So for the constant K sub P. Now you might remember that your constant, you may have been using K sub C for a lot of your reading material, because that is the equilibrium constant based on the concentration of different substances. And I'm going to go ahead and pause this so that I can bring something into this and come back. Okay, so I know you didn't see me take time to pause this, but what I've just thrown up on the screen is a clip from the AP formulas and equations resource sheet, which is something that you are going to want to have with you when you are taking the test, and you probably want to have it around or have access to it anytime you are working on these free response questions, because for each section of material, there's a whole bunch of stuff available to you that might make it very easy for you to answer some of the questions without having to think too hard or remember back to what notes you may have taken or assignments you may have done. Okay, so here's the example of the section on equilibrium. I want you to notice that they show several different types of equilibrium constants, and they give you the general formula for how to set it up where you have a balanced equation. So you don't even have to remember that you put the products over the reactants. You can just look at the sheet if you're trying to remember which one goes on top. Okay, so make sure that you are making use of this when you are solving these problems, and particularly when you're taking the test. Definitely get yourself familiar with it now before the test. Okay, so Kc, which is the one that you may have spent the most time looking at, is based on concentrations. And this is going to be in an aqueous solution, okay? So this is equilibrium in an aqueous solution. And this is going to be related to the concentration of the different substances, your reactants and products in the solution. So that's what the brackets around the substance means. That's a symbol for concentration. And so it's the concentration of the substance raised to the power of its coefficient in the balanced equation. And so this may be what you are familiar with. This is what you guys used when you were doing the equilibrium reading assignment to give the equilibrium expression to the equation that I gave you. This is exactly the same thing, but instead of concentrations, it's using pressures. So instead of C in brackets, we have the pressure of C, in parentheses raised to the little c power, the pressure of D raised to the little d power. So this is going to be what you're going to use when you have gases reacting, okay? This is what you're going to be using when you have reaction in a solution. These three have to do with acid, base, and the dissociation of water. So I'll try to cover a little bit about that next week when we go into our intro to acids and bases. Okay, so just realize, and it even tells you that this is molar concentration, so you know that this is moles per liter, this is gas pressures, etc. And so if you forget how to do this, you can go back to your formula sheet and find a lot of this information there. Okay, long digression, but it's important. Okay, so we need to write an equilibrium expression for this equilibrium constant for this reaction. So we are going to write K sub P equals, and it's going to be a fraction, and it's going to be the products over the reactants, and we're not doing brackets because this is not concentration. We're talking about the pressure of different gases. Okay, so the pressure of CO, carbon monoxide, is going to be on top, and that is going to be raised to the second power, or squared, because there's a 2 in front of the CO. That's the coefficient for the carbon monoxide. Okay? And then the denominator is going to be the pressure of the CO2, and that would be raised to the power of 1, because if there's no coefficient in front of it, you know that there's an invisible number 1 there. And here, it's not wrong if you put this raised to the 1 power, but that's also superfluous. You don't need to say raised to the first power, because anything raised to the first power is itself. Okay, but if you put that, they're not going to mark it wrong. All right. So this is ideally what your equation should look like. Try to be careful not to use the square brackets for concentration when you are talking about pressure, and vice versa. Make sure you are using the square brackets when you're talking about solutions, aqueous solutions. Okay. So this is your expression. That's all there is to it. Okay. So let me think. I'm just looking at my notes to see if there's anything else I want to talk about here. I think I covered that. Oh, yeah, one more thing. Why do I not have the solid carbon on the bottom? That's also a reactant. How come I don't have a P sub C down here? The reason for that is that the solid carbon doesn't have a pressure. Okay, it is not a gas, and the amount of solid carbon is considered to be negligible, so we don't actually include anything about the solid carbon in terms of the equilibrium expressions here, because the solid is not really getting involved in this, particularly because we've been told that there is sufficient of the solid carbon to get us to whatever amount of reaction we're going to have, forward reaction we're going to have. Okay. So when you're talking about pressures, you're only talking about the gases. Okay, so that's the answer to letter A. Letter B says calculate the number of moles of CO2 initially placed in the container. And here, again, it says, assuming that the volume of the solid carbon is negligible. Okay? Now, that's a key here. So that's a clue that volume of your CO2 is going to be important. Okay? Because the volume of the solid is negligible. We have one measurement of volume in our question, which is the 2.00 liters. Notice that this is 3 significant figures. So make sure that you are keeping track of your significant figures as you go through these calculations. Your general best practice is to not round anything until the end, but just keep track of the limitations on that. And I will throw up a great link or PDF about significant figures for you guys in my MCPS classroom as soon as I get a chance to. Okay, so we've got a measurement of volume here, and it's asking us for the number of moles. And you know that we have total pressure, and we know already discussed how this 5 atmospheres is the initial pressure of our CO2 at the beginning of the experiment when we put it in the container along with the solid carbon. Okay, so we have pressure, we have volume, and we're looking for moles. And by the way, we also have a temperature given to us in our question. So if you haven't figured out already that we are using the ideal gas law, you need to go back and review the gas laws unit. And guess what? The ideal gas law is also on the AP formula sheet, so you don't even have to have it memorized. It's there for you. You just have to know to look at it in the gases section. So ideal gas law, PV equals nRT. Okay. Okay, I paused it again so that I could pull this out of the formula sheet as well. So here is our the section on gases, liquids, and solutions, and you can see that our PV equals nRT is right here. I also want to point out, in case most of these are, in fact, all of them are written here in case you've forgotten what they are. Okay, so P is pressure, V is volume, T is temperature, N is number of moles. And if you are looking for R and you scroll down, you say, oh, R is the gas constant, right? And notice that we have 3 different versions of the gas constant, because depending on how we are using it, in what context, we're going to use different ones. Now, the best way to figure out which version you're looking at is to figure out what units you already have, okay? Because the gas constant, being a constant, has a bunch of units to basically counteract the other units in an equation. So we have temperature in Kelvin, we have volume in liters, we have pressure in atmospheres. So if we look in these 3 versions of R, we see that one of them has liters atmospheres per mole Kelvin. Okay, and that is the one that we are going to use in this problem. Okay, so we've what we're going to do here, we're asking for number of moles. I'm going to go ahead and rearrange this equation so that we are solving for N. So N is equal to, it's going to be our pressure times our volume over the gas constant times temperature. So our pressure is 5 atmospheres times our volume, which is 5.00 atmospheres. Our volume is 2.00 liters. Our R in this case is going to be 0.08206 liters atmospheres per mole Kelvin. Okay, that's 0 point there. This is an example of where you would not round this until you get to the end of the problem. So you are given this number of significant digits for your R in this case. So go ahead and plug that number of significant digits into your equation, and we'll round the end result to the nearest 3 significant figures. Okay, and then our temperature is the other part of our denominator, and that's going to be our 1,160 Kelvin, which if you remember back to significant figures, that final 0 is not considered a significant figure. So this is also given to us in 3 significant figures. Not that it matters, because since even if it were 4 significant figures, our atmospheres and our liters are both given to us in 3, so we would have a maximum of 3 significant figures in our answer. So we've got 5 times 2 divided by this number times 1160. What we end up with is 0.10505, and it keeps going on your calculator. But again, we are rounding to significant digits. We're rounding to the 3rd significant digit. And so we look at the one afterwards, and we see if it is bigger or smaller than 5. It is less than, so we go ahead and round to 0.105. And please, 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 for all of these questions, make sure that if there are units, that you write them in the answer. So you could write n equals 0.105, and you may not get full credit for it if you do not also put moles, okay? Even more specifically, you could put moles of CO2. I don't think that's necessary. As long as you indicate that you know that this is in moles, you're fine. And if you write out the word moles, that's also fine. MOL is the traditional abbreviation for that. Okay, so that is the answer to letter B. Okay. I have been trying to find out how strict the AP is, how strict the readers are about grading significant figures for the AP exam, and I'm still trying to get that information. I have some old blog posts from people who used to read the exam saying that they were, plus or minus 1 significant figure, they would give you the credit, but I wouldn't count on that. I would try to get to the proper number of significant figures throughout these problems, just to give yourself the best chance of getting a full score. And I also don't know for the AP whether significant figures are, for the IB, it would give you minus 1 point across the entire section. I don't know if that's true for the AP or not. I'm still figuring that out. Okay, so that is the answer to question B, part B of question 1. So now we move on to part C. So same stuff from the question as I've just repeated it up here. So for part C, it says, for this reaction mixture at equilibrium at 1160 K, the partial pressure of the CO2 is 1.63 atm. Now, if you remember from the gas laws, back from the FET and from the other questions that we worked on, your total pressure is equal to your partial pressures, the sum of your partial pressures of whatever gases you have in your mixture, okay? So we have, it says at equilibrium, so that's down here. That is the pressure, this is the total pressure at equilibrium, 8.37 atmospheres. Okay, and it says the partial pressure of the CO2 is 1.63. So letter I is just, you're going to have 8.37 is equal to 1.63 plus the partial pressure of CO. And so if you solve for pressure of carbon monoxide, you should get I'm reading the wrong number here. You should get 6.74. And again, make sure that you write the units. 6.74 atmospheres. You do not want to lose points for not writing your units down. Okay, so that's easy. And then the next thing it asks is for the value of Kp. Well, we already figured out the equilibrium expression for Kp. So we're just going to, we don't have to do anything fancy here, any kind of fancy calculations or anything like that. All we need to do is plug these values into our equation from part A. So our equation was Kp equals the pressure of carbon monoxide squared over the pressure of the carbon dioxide. Okay? So that is going to be equal to 6.74 squared over 1.63, not squared. And if we do that calculation, that's going to be 27.869, etc. And again, we need to look at the numbers that we have, and we have 3 significant digits. So we're going to take a look at our 4th digit, and that is higher than 5. So we're going to call this 27.9. Now, what are the units for an equilibrium constant? The answer to that is they don't have units. All right, so this is the one situation that I can think of off the top of my head where you do not need to put units in your answer. That is just the answer. 27.9 is the value of equilibrium constant for pressure. Okay, and next we have a question which is very similar to a question that was on your reading check, so you should all be able to answer this one pretty easily. It says, if a suitable solid catalyst were placed in the reaction vessel, would the final total pressure of the gases at equilibrium be greater than, less than, or equal to the final total pressure of the gases without the catalyst? And it says justify your answer. So you have to give you can't just say greater than, or less than, or equal to. You also have to say because why. Okay, so this is kind of like when you're writing your test corrections, and I don't let you just give me the correct answer. I need you to prove to me that you actually know why it's correct. That's very similar to what you're going to do for any question that asks you to justify it. Okay. There's a couple things, or one thing of interest in this question. It specifically says a suitable solid catalyst. Think for a minute why they have to say in the question, why they have to specify that it's a solid catalyst. So the answer to this is very similar to the reason why we don't pay attention to the solid carbon in our initial reaction when we're looking at the equilibrium. If it is a solid catalyst, it is not going to appreciably change the pressures in the containers, and so it's not going to have an effect on that beyond its effect on in terms of catalyzing the reaction itself. The presence of the catalyst is not its volume is not going to be contributing anything to the pressure of the system, at least not at the level that we're calculating. So that is important that they say that it's a solid catalyst. And when they're asking whether the pressure would be greater than, less than, or equal to, remember, let me go back to our equation here. I didn't put it on this one. So remember that the pressure is going to be dependent on the relative mixture of our reactants and our products, because we're going to have a higher partial pressure of our carbon monoxide compared to our carbon dioxide as we move forward in this reaction. So because of the 2 moles versus 1 mole. More moles of gas equals more volume or more pressure if we have a fixed container. And that's the other reason why it has to specify a rigid container, because that tells you that we cannot change the volume, we can only change the pressure. So are we going to, basically what this question is asking is the catalyst going to change the equilibrium? And as I think everyone whose reading check I graded said in their answer to that question, no, it will not change the equilibrium. It will change the rate of reaction. So remember that if we're looking at an energy diagram from the previous unit, and we have our reactants and there's an activation energy, and then we end up with our products, this this activation energy is what is acted on by a catalyst. So the catalyst is not going to change the equilibrium. It's not going to change whether we have more reactants or more products. What it's going to do is it's going to get us to equilibrium faster by lowering that curve so that it takes less energy for the reaction to proceed. And notice that whether we're going in the, in the forward direction, it's lower. But also, if we think about it as taking the reaction in the reverse direction, it similarly lowers the threshold, okay? So it's lowering the threshold for both directions of the equation equally, and so that is why the catalyst is not going to change the equilibrium. So you would say the final total pressure would be equal. And I don't think you have to be super careful about grammatical correctness here, or even complete sentences. They're not going to take points off for grammar as long as you are clear. They might take points off for clarity if your writing is such that they don't understand what you're saying. Okay, so try to be as clear as possible and as concise as possible while getting everything across. Would be equal because the catalyst would decrease activation energy in both directions. Or you can, and there's a lot of ways you can word this. This is just an example. Leaving Kp unchanged. So your catalyst is not having any effect because it's a solid. You could even also say that it's a solid catalyst, so it's not going to have any effect on pressure, and therefore it's not going to have any effect on Kp. So so there's, you have to say basically if there's no change in pressure, and because there's no change in the composition of the mixture at equilibrium between the non-catalyst versus catalyst version. Okay, so however you want to write that is up to you. And I'm pretty sure I gave you the ability to read the answers, which includes the scoring guides on AP Classroom for these questions. So you can also look at what AP specifically says, their specific wording. They are not as specific as the IB mark schemes are for a lot of these questions, but you can still get a pretty good idea of where you might get partial credit for some questions. Okay, so that's D. We have one more section left. Section E. So now it says there's another experiment involving the same reaction. So we have the same reaction happening. We have a 2-liter container. And now it's telling us that we specifically have 10 grams of carbon, plus we're starting with some carbon monoxide already in the container, as well as carbon dioxide. Okay, so we've got something that is not the same. Our initial starting mixture is a mixture of gases, not just the carbon dioxide gas like we did in the previous example. It says that each of our gases are at a partial pressure of 2 atmospheres. So rather than having just CO2 at 5 atmospheres like we did in the initial reaction, we have carbon monoxide at 2 atmospheres and carbon dioxide at 2 atmospheres. And that its temperature is the same. So our volume is the same, our temperature is the same, but our pressure is different and our mix of gases is different. And now letter E says, predict whether the partial pressure of carbon dioxide will increase, decrease, or remain the same as this system approaches equilibrium. And then it says justify your prediction with a calculation, okay? So we can just think about this for a minute, and we can say, okay, if we're looking again at our react balanced equation, let me just go back to this here. So we've got our solid carbon, our CO2 gas, and our carbon monoxide here. And again, this is going to go back a little bit to our molar ratios. So if both of these have equal pressure, okay, that means that they both have equal moles in this system, okay, in this new version, all right? So if you think about the same number of moles of carbon dioxide and moles of carbon monoxide, you know, what are we going to try to get to in terms of which direction is the equilibrium going to go to? The reaction should be shifting towards the lower number of moles of gas, and therefore the lower pressure. That is the part of Le Chatelier's principle, is that if we change things like pressure, temperature, or concentration, we're going to shift the equilibrium in one direction or the other. Okay, so if we are adding essentially our product, some of our product, then we are going to be shifting back in this direction, because the more carbon dioxide we have, the lower the pressure is going to be, and so the reaction is going to be favorable in that direction. I mean, up to a certain point, okay? So we can imagine in our heads, without even doing a calculation, that we're probably going to be increasing the pressure of our carbon dioxide, given those new initial starting conditions. But we need to do a calculation. What kind of calculation can use our initial pressures? So we're given initial pressures of our gases, rather than being given initial pressure of one gas and then the equilibrium pressure of the combined. We're now getting the initial partial pressure of each gas. And so think about, for a second, about what calculation we could do, what variable we could calculate that might tell us something about the direction of this reaction under these conditions. So this is a situation where you're going to be calculating Q, which is your reaction quotient. So your Q is going to be based on your initial concentrations or your initial pressures, okay? So you're going to set it up exactly the same way you set up your K sub P, with the products on the top and the reactants on the bottom, with the coefficients as the exponents. But in this case, we're using our initial pressures, okay? So our Q is going to be 2.00 for the pressure of, sorry, let me write out the formula first. So it's going to be our partial pressure of carbon monoxide squared over the partial pressure of carbon dioxide, okay? But again, these partial pressures, we're now getting them not from the equilibrium, but from our initial, which is why this is a Q and not a K. This is going to give us 2.00 squared over 2.00, because they're both at partial pressures of 2 atms. And so that is going to give us 2 squared over 2, which is equal to 2. Okay, and again, this does not have a unit, okay? So our Q, sorry, hang on a second. Okay, so our Q is 2, all right? If our Q is 2, and we previously measured our Kp as 27.5 oops, not 72. I'm not really dyslexic. 27.9. That means that our Q is less than our K. I cannot even write here, sorry. Q is less than our KP. That means, as most of you correctly wrote on your reading assignment, that means that we will end up with the mixture shifting towards the reactants, or shifting to the left. And so that, since we're starting with, since CO2 is our starting reactant on the left, we are going to be increasing the amount of CO2 that we're producing, so the partial pressure of CO2 will increase. Okay. All right, hopefully this all made sense. Hopefully, after reviewing this, if you didn't already know how to solve these equations, you will be able to do so in the future. I am going to do another one later, probably over the weekend, that includes having to use a Rice table to calculate your equilibrium constant. So look forward to that. And please be watching those AP classroom videos or AP YouTube videos. They're great. It's a great resource. And it's far more than I would have time to put together for you right now. So I'm really glad that they have this up there. All right. Talk to you guys soon.